This is the beginning of Unit 5, and we're going to start an entirely new topic in this unit. We're going to begin talking about algebraic sequences and series. And this is going to take us through Unit 5 in Chapter 8, as well as Unit 6 in Chapter 9. So we'll begin with our discussion of sequences. This is material out of sections 8.1 and 8.2 in your book. A sequence is simply a list of numbers. Mathematically interesting sequences are not usually random lists. Usually they have some kind of a pattern that allows us to predict additional numbers in our sequence. A little bit of vocabulary that's associated with our sequences. First of all, each number in the sequence is called a term of the sequence. And sequences can be denoted in a couple of different ways. We can list out the terms, the first term, second term, third term, and so on. Or we can just say it's the set of all the terms, a sub n, and then we have to give the first value, and then if it's an infinite sequence, which the ones we're looking at mostly will be, it goes all the way to infinity. Oftentimes, because this is sort of understood that we start with our first term and we go on forever, we sometimes just leave that off and kind of use the shortcut or shorthand notation, just the set of a sub n. That little subscript, that n that appears, is called the index. So you have an index of 1, an index of 2, and 3, and so on. So let's look at a few examples of sequences. I've got the sequence here to start with, 2, 6, 10, 14, 18, and so on. And just to get used to the vocabulary, what is the second term of the sequence? That would be the 6 right here. And if I asked you, what is a sub 4? That would mean the fourth term. So 1, 2, 3, 4. That would be the 14. All right, what are the next 3 terms in the sequence beyond what's shown? This is where you start analyzing the pattern. And I'm sure by now you've taken a look at this and recognized that each time we're adding 4 to get to the next number in the sequence. So if I were to add 4, I would get 22, and then add 4 again, 26, and add 4 one more time, 30. And that would be the next 3 terms. All right, we can specify a sequence in 2 different ways. We can write it as what's called a recurrence relation. A recurrence relation gives a formula for each term as a function of the previous term or terms. So based on a sub n, we get a formula for a sub n plus 1, the next term. When we said to go from one term to the next, we were adding 4, we were describing a recurrence relation. In this case, we would have said, well, actually, we're going to do it down here. Sorry, let me do the other one first. If I wanted a recurrence relation for the sequence, adding 4 to get from one term to the next, what I would say is a sub n plus 1 is the previous term, a sub n, plus 4. So there's my recurrence relation for our sequence. An explicit formula gives an actual formula for each term as a function of the index n. So a sub n is f of n. Let's see if we can find an explicit formula for this sequence. My advice here is it sometimes really helps to make yourself a little table of values. If my index n is the input, and the term a sub n is the output, the first term was 2, second term was 6, third term was 10, fourth term was 14, and so on. So I might say This looks like a linear function to me, right? All the slopes are the same. The increase in the x always goes up by 1, and for the y it always goes up by 4. So if I think of this as a linear function, kind of like a y equals mx plus b, I can see that the slope would be 4, right? The change in y would be plus 4 when the change in x is plus 1. So my slope is 4 over 1, or 4. And I could kind of predict backwards. If I'd had an n of 0, I would have had to have subtracted 4, so that would be a minus 2. That would be the b value. So my function, instead of y, we have a sub n, is going to be the slope 4, and instead of x, we have n, plus the b value, negative 2. So two different ways to describe this sequence. We had the recurrence relation, each term, add 4, get to the next term. And then we have the explicit formula. If I wanted, a specific term, if I wanted the 4th term, I would just plug n equal 4 in. 4 times 4 is 16. 16 minus 2 is 14. And that would just give me that 4th term right there. All right, is there an advantage of one way of specifying these terms over the other? Is there an advantage of the recurrence relation or the explicit formula? Here's a hint. What if in this sequence I asked you to find a sub 20? How would you have to do that in each case? Well, if I wanted to do it using the recurrence relation, to get a20, I would need to know a19, right, to add 4 to. So basically, if I wanted to use the recurrence relation, I would have to list out all of the terms up to the 20th term. Using that pattern of adding 4 each time. And I'm just going to quickly go through and do that. What am I at? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. There we go. So there is the 20th term in my sequence. Kind of a pain, right? Thank goodness I didn't ask us for a 100. Now let's look at doing this using the explicit formula. Well, now if I want a20, I know the index, or the n value, is 20. I can plug that into my formula. And that would be 80 minus 2 is 78. So looking at both methods, I think you can kind of see the advantage in having an explicit formula. We don't have to actually build our way up. We don't have to know all of the terms leading up to the one we want. Instead, we can isolate it and just get it by itself. So that's kind of nice about the explicit formulas. All right. Unfortunately, they aren't always possible to find, usually, but not always. So let's take a look at a couple of examples for each of these types. We'll take a look at some explicit formulas and some recurrence relations. Right? Again, in general, it might be challenging to come up with workable recurrence relations and especially explicit formulas. But we're going to start by examining some that we kind of know. And I think you're going to see some patterns here that we'll be able to use later when we want to come up with our own. So, in example 2, we've got some explicit formulas. And the instructions are to simply find the first 5 terms of the sequence. So I just start by plugging in n is 1. And then the next term would have an n of 2, and so on, until I get to the 5th term, plugging in n equals 5. And of course that would keep going, but I only have to find the first 5. So I get 1/2, 1/4, 1/8, 1/16, and 1/32. All right, this next one is just kind of a short hop from the one we just did. Instead of 1 over 2 to the n, I have -1 to the n over 2 to the n. Let's take a look at what happens with that -1 to the n, because this is something that's going to occur somewhat frequently. So if we can kind of identify what it does, it's going to help us out. I'm just going to start again by plugging in first an n of 1, and then an n of 2, and so on. And of course the denominators are exactly the same as they were in the first example. But look at what happens to the numerators. -1 to the first is -1. -1 squared, of course, would be +1. -1 cubed is -1 again. -1 to the fourth is +1. And lastly, -1 over 32. So what's happened is all of the values of the original sequence are the same in terms of absolute value. In the second sequence, that -1 to the n simply caused these terms to have alternating signs. Just to emphasize, I'm going to put pluses on the ones that are positive. And notice how every other term is positive and every other term is negative. This structure causes what we call an alternating sequence. Where the terms just change signs from one to the next. All right, C. We want 2n plus 6 to be our explicit formula. So once again, I'm just going to plug in 1, 2, so on. And I'm going to get 8, 10, 6 and 6 is 12, 8 and 6 is 14, and 10 and 6 is 16. And you'll notice that, once again, all of these are increasing by the same amount, specifically 2, and I've got that linear function, kind of like the one we looked at on the previous page, so that's something to keep in mind. All right, one more example here. Our last explicit formula is n plus 1 over n. So once again, I'm just going to start by plugging in all my values. Plugging in 1 and 2. Oops, should have been a 2 plus 1/2. And then a 3 plus 1/3. 4 plus 1/4. And 5 plus 1/5. All right, 1 and 1 is 2. 2 1/2, otherwise known as 5/2. 9 1/3 would be 10/3. 16 17/4. And 26 25ths. Sorry, just 26/5, not 25ths. Got a little bit overboard there. There we go, 26/5. All right, so those are our explicit formulas. And again, it's really as simple as just plugging in the values. On the next page, next example, we're going to look at some examples of recurrence relations. So given each recurrence relation and value of A1, find the next 5 terms of the sequence. Notice that because each term of a recurrence relation depends on the previous term, you have to have a starting term. Otherwise, you have nothing to perform the recurrence relation on. So in this case, we've got A1 is given to us as 5. And then the recurrence relation says, to go to the next term, take the previous term and add 7. So 5 being our first term, the given, 5 plus 7 would be 12. And then 12 plus 7 would be 19. 19 plus 7 is 26. Adding 7 again gives me 33. And one more time gives me 40. So I've got 1, 2, 3, 4, 5 more terms. But again, to go from one term to the next, the recurrence relation just tells me to add 7 each time. All right, what about the next one? In part B, they tell us the first term, A1, is 1. So there's where I start. And then it tells me, once I know a term, to go to the next one, multiply by 4. So multiplying by 4 is going to give me 4. Times 4 again is 16. Continuing to multiply by 4, I'll get 64. What is that? 256? Is that 10, 12? I think so. Yeah, 1024, sorry. All right, let's take a look at another recurrence relation. In this next one, they tell us that we're starting with our first value, A1 is 2. And this time, to go from the next one term to the next, we square our previous term and subtract 1. So this time I'd have to go with 2 squared minus 1. 4 minus 1 is 3. And do it again. My new term is 3, plug that in. 3 squared minus 1, 9 minus 1 is 8. Let's keep going. 8 squared minus 1 would be 63. And then 63 squared minus 1 is a pretty big number. 3968. And so on. So that's recurrence relations. You always have to know the previous term to get to the next one. All right, in the last example here about recurrence relations, example 4, I have an example where the recurrence depends not just on the previous term, but actually on the 2 previous terms. In this case, they've given us the first 2 terms. In this case, we're starting with an n of 0, so a sub 0 or a naught is equal to 1. And a1 is also equal to 1. So our first 2 terms are both 1. Now the recursion formula tells us to get to the next term, add the 2 previous ones. Add a sub n, and then the one before that, a sub n minus 1. So if I add these 2 terms, 1 plus 1, I'll get to the next one, which is 3. I'm now going to add the 1 and the 3. Excuse me, I'm going to add the 1 and the 2, giving me 3. and then add the 2 and the 3, which is 5. The 3 and the 5 giving us 8. The 5 and the 8 giving us 13, and so on. So a recurrence relation doesn't necessarily have to depend only on the previous term. It could actually depend on multiple previous terms. This, by the way, is actually a really famous sequence. It's called the Fibonacci sequence. Fibonacci was a famous mathematician, and this was a sequence that he did quite a lot of work with. It's kind of an interesting one. There are a lot of numbers in nature that occur using these Fibonacci numbers. If you look at things like the number of petals on a flower is almost always a Fibonacci number. The spirals of a pine cone, the number of spirals is a Fibonacci number. So these numbers just occur in nature all the time. All right, so we've looked at both some recurrence relations and some explicit formulas. We're now going to turn the tables and go the other way. We're going to say, if I give you a sequence, could you find both a recurrence relation and an explicit formula? We'll try to do both, if we can. There may be times that we'll have to say, I can only find one or the other, but not both. But let's see what we can do. All right, in this first one, and I think what I'm going to do is I'm going to do the recurrence first, and then the explicit. Right. Looking at this first sequence, I can see that the pattern seems to be adding 3, right? And that seems to continue to work. So the recurrence relation is somewhat obvious. To go from one term to the next, we add 3. So how are we going to write that? Well, first of all, I have to tell you the first term. A1 is 3. And then we're going to say, to get to the next term, A sub n plus 1, we take the previous term, A sub n, and add 3. To get the explicit formula, we might want to again think of this in terms of an input-output set. The first term is 3, second term is 6, third term is 9, fourth term is 12, and so on. And I can see that the slope here would be 3 over 1, right? 6 minus 3 is 3, 2 minus 1 is 1. The y-intercept, and again, the easiest way maybe is just to sort of use this little pattern to predict backwards. If n were 0, I'd have to subtract to go backwards. So subtracting 3 would give me 0 as well. So b is 0. And my an is just 3 times n plus 0, or just 3n. So there's both a recurrence formula and also an explicit formula. All right, let's try a few more. Next one. If you look at the pattern here, to go from one term to the next, we're multiplying by 3, right? 4 times 3 is 12. 12 times 3 is 36. 36 times 3 is 108, and so on. So this time for my recurrence relation, instead of adding 3, we're going to multiply by 3. Again, I got to give you somewhere to start. So I'm going to tell you the first term. A1 is 4. And then A sub n plus 1 is 3 times A sub n. All right, what about an explicit function? First term is 4. Second term is 12. Third term is 36, so on. And again, with that pattern being times 3, this is going to be an exponential function, right? The exponential pattern is that when the x values go up by the same amount, the y values have a constant multiplier. So I'm already thinking the form y equals ab to the x. My y's are the a sub n's. I don't yet have a value for n of 0, but again, I could use this pattern and just predict backwards. Since pattern down is times 3, to go backwards I would divide by 3. So 4/3. Times the b value 3. To the, our x is actually an n value. Again, all of these have been assuming that I want to start with an n of 1. That's an arbitrary choice. I could have said, hey, I want to start with an n of 0, and I could have put 0 in first. But unless we specify otherwise, we're always going to assume that we start with an n of 1. All right, next one. I have got 5 and 1, 1/5, 1/25. This is going to be another multiplier, right? You can think of it as dividing by 5, but it's going to be easier if I think of that as multiplying by a 5th to go from one term to the next. So, if A1 is 5, then AN plus 1 is going to be AN times 1/5, or I could just write that as A sub n over 5. Same concept over here. With a constant multiplier like this, I know I'm looking for an exponential function. So let's see. Y equals ab to the x. And I would have my y's are my a sub n's. Again, if I kind of think backwards, if n were 0, let's see, I'm dividing by 5 going this way, I'd have to multiply by 5 going that way. So that would give me a 25. So that's my a value. Times the b. The base is that constant multiplier, times 1/5, right? Raised to the x or n power. All right, one more. On this next one, I have got an alternating sequence. Notice how it goes negative, positive, negative, positive, negative, etc. And on this one, although I claim if we worked really, really hard, we may be able to come up with something kind of like a recursion formula. On this one, the explicit formula is actually easier. First of all, we saw before that in order to get the signs to alternate, we had to use a factor of -1 to the n. Right? That way, when n's are odd, we get negatives, and when n's are even, we get positives, which is exactly what we want, right? First, third, fifth term will come out negative. Second, fourth, etc. will come out positive. Just a comment, had that been reversed, had we gone positive first, I just would have put an n plus 1 up here, and that would have fixed it. All right, If you now ignore the negative signs, because we've got those taken care of, what do you notice about all of these numbers? 1, 4, 9, 16, 25. All perfect squares, right? So that's going to be times n squared. All right, a recurrence relation for this one, it's only sort of a recurrence relation, the best I'm going to be able to come up with. There's actually a little bit of an element of the explicit formula as well, so it might be called a hybrid format in a way. I'm going to tell you what works, although this is not necessarily what I think of having you come up with necessarily. This is not going to be very convenient. Alternating series rarely are. Here's how I could sort of make it work. I could say a sub n plus 1 is the square root of the absolute value of a sub n, then add 1 and square it, and then I'm still going to have to make it alternate by writing a times -1 to the n. Excuse me, I think that's when I'm actually going to have to be n plus 1 because it's the n plus first term. Okay. Let's just look at what happens. And I'm going to start with the second term, the 4. Okay. If I take the square root of 4, that's 2. 2 plus 1 would be 3. 3 squared would give me the 9. And then if n is 2, 2 plus 1 is 3, -1 to the third would make that 9 negative. So it does work, but the fact that I've actually used n in the formula makes this kind of a hybrid. It's part recursion. This part is definitely a recursion formula, but this little piece is actually an explicit piece of the formula as well. So it's kind of a mixture. All right. All right. So I want to go ahead and talk a little bit more about vocabulary, terminology associated with sequences. We say that a function a sub n, or excuse me, a sequence a sub n, is increasing, literally if each term is bigger than the one before it. So mathematically, we would say a sub n plus 1 is bigger than a sub n. Easy example of an increasing sequence, just the counting numbers. 1, 2, 3, 4, 5. Each term is larger than the previous term. Non-decreasing, we simply allow for the possibility that 2 terms in a row are equal. So a sub n plus 1 is greater than or equal to a sub n. Good example of a non-decreasing sequence is the Fibonacci sequence. Okay. Notice that the first 2 terms don't technically meet the definition of increasing. The second term is not bigger than the first, but it is greater than or equal to. So we can call this one non-decreasing. It's not necessarily strictly increasing, but at least it never decreases. All right, we have those same definitions only backwards for decreasing and non-increasing. In a decreasing sequence, every term is less than the one before it. So a sub n plus 1 is less than a sub n. Here's an example of a decreasing sequence. 1/2, 1/3, 1/4, 1/5. Each of those fractions is a little bit smaller than the previous one. Non-increasing again simply allows for the possibility that the terms may be equal to one another. So every term is less than or equal to the previous term. Just for fun, take a look at this one as an example. It's a boring sequence. Every single term is 2. But notice that it does fit the definition of non-increasing. Every term is less than or equal to, especially equal to, the previous term. In fact, this is also non-decreasing because every term is greater than or equal to the previous term. So this one happens to be both. Monotonic. A monotonic sequence is either non-increasing or non-decreasing. Essentially, it means it goes all in one direction. Mono meaning one, right? So all in one direction. Either non-increasing, meaning it basically always goes down or maybe stays the same, or non-decreasing, meaning it always goes up or stays the same. Here's an example of a monotonic sequence. All the squares, 1, 4, 9, 16, 25. Notice that if I made this into an alternating sequence, 1, -4, 9, -16, 25, and so on, now it is not monotonic. It goes down and up, right? Doesn't always go in the same direction. Not monotonic. All right, the last one, bounded. We say a sequence is bounded, and I'm going to give you the mathy definition first, and then we can really talk about what it means. If there is a number m so that the absolute value of a sub n is less than or equal to m for all n. In other words, there's an upper limit to the absolute values of the terms. There's some number that bounds or limits every single term. Here's what we looked up there. 1/2, 1/3, 1/4, 1/5, and so on. Notice this is definitely bounded. As these fractions go on, they're all going to get smaller. So in fact, every single term is less than or equal to 1/2. This is bounded. Compare that, say, to this alternating sequence here. Right? The absolute values of these just keep getting bigger and bigger and bigger. There is no largest value, so this one would be unbounded. All right, so that's just a basic definition or basic introduction to some of the definitions that surround the ideas of sequences. We've looked at recurrence relations as one way to define them, explicit formulas as another way to define them, and then some of this vocabulary that goes with it. In the next installment, next video, we're going to start looking at how to find the limit of a sequence. So I'll pause here for now.